Now let's discuss how physical laws should appear, or the form that physical laws should take in order for them to be compatible with Lorentz transformations. Okay, so what we mean by that is if you take any physical law and you ask what this looks like as seen by a particular observer or a particular reference in a particular reference frame S, and ask what this looks like in a different reference frame S prime, the form of the physical law to both these observers should appear to be the same. So both observers should see the same form of the physical law. Okay, where S and S prime are two inertial observers. Okay, if they do not see the same form of the physical law, then what that would mean is that one observer would have a way to tell that they are different from a different observer. Okay, so there would be a way to identify different states of relative motion. So the fact that no inertial observer can tell that they are special means that each inertial observer has to see exactly the same form of the physical laws. So remember that they may measure different things for velocities, accelerations, and so on, but they all have to see exactly the same form of the physical laws, otherwise they will know that they are in a special reference frame. Okay. So what do we mean by the same form of the physical laws? What that means is, suppose we have a physical law where we equate one quantity with another. So this is the left-hand side of a physical law, and this is the right-hand side of a physical law. And the physical law tells us that these two quantities have to be exactly the same. Okay, so for example, in Newton's law, this is F is equal to ma. In Maxwell's equations, it relates derivatives of the electric and magnetic fields to charge and current densities. Okay, so now the important point is that if I calculate this in some reference frame S, okay, the form of this law should take exactly the same form in a reference frame S prime, where I appropriately transform the left-hand side and right-hand side. Okay, so using my dictionary. So my dictionary tells me how to relate the left-hand side of this equation to the left-hand side of the equation in frame S prime. And the right-hand side, I can also figure out using my dictionary how to transform it into the right-hand side in frame S prime. Now, the important point is that the form of the physical law should remain exactly the same. Okay, so since we've seen that the most general way to describe dictionary objects that transform under special relativity transformations is to use tensors, if the left-hand side of a particular equation is described by a particular tensor quantity, okay, so let's assume that this is, let's say, a rank n tensor, and the right-hand side is a different rank n tensor. So let's call this a mu1 to mu n. The physical law is telling us that this tensor, if I calculate each of its components in frame S, that should be related to this other tensor where I calculate each of these components in frame S. In frame S prime, we know the transformation rule, which will relate this tensor to a new tensor. Okay, T prime. And similarly, A will be related to a new tensor. So what we see is, under Lorentz transformations, if the laws take this particular form, where one tensor of rank n is equated to a different tensor of rank n, In the frame S prime, the laws will take the form where the corresponding transform tensor of rank n is equated to the corresponding transform tensor of rank n. Okay. If this is true, we say that the laws in frame S prime take exactly the same form as the laws in frame S. Okay, it's just the same tensor T is equated to the tensor A. It's just that you have to use a different or transformed tensor T, T prime, and a different transformed tensor A prime. This would not be true if in a physical law, the left-hand side of the equation was not a fixed tensor. Okay, that is, supposing I had something like U alpha. Okay, and to this, if I take U0, I add U0 plus M. And if I have U1, I add U1 plus E, let's say. Okay, or things like this, where the quantities here transform as components of a 4-vector, but the quantities that I'm adding here are, let's say, 4 scalars. Now, the left-hand side of the equation doesn't have a well-defined transformation law. That is, each part of it has to be transformed separately when I go to frame S prime. Okay. And so now when I do this, what I would find is if I do not have a well-defined tensor on the left-hand side of the equation, a well-defined tensor of a particular rank, then the law will not take exactly the same form in frame S prime. Okay, and therefore we would have a way to distinguish between these reference frames because the laws do not appear to take the same form. Such a law would be incompatible with the law of the dictionary of special relativity. Okay, so finally we can say that for any physical law, the important thing to be compatible with the dictionary of special relativity is that it should take the form that if I have a tensor of rank n on one side, I should have a tensor of rank n on the other side of this equation. And this is the only way in which this law would be compatible with the dictionary of special relativity.